First question is about the urban heat island effect. So we talked about this the other day. It's a potential thing that could be biasing potentially the land temperature record. So it's something that people think about and worry about who are trying to assemble temperatures of the Earth from the thermometer data going back, the instrumental record they call it. So is the urban heat island effect an urban legend? I mean, is it just, wrong? Or is it a real effect, but not significant to the global average temperature? Or does it significantly contribute to the global average temperature as measured by thermometers? Well, so the urban heat island effect does have credibility, but it actually, so B is the correct answer here. It turns out, I mean, the way they try to deal with this is they have this morass of all this meteorological data and some particular locations, if they're worried that they might be sort of biased by urban heat island effect, which is that, it's always hotter in cities than it is in the countryside. They just sort of get rid of that data point, and so a lot of so there have been many compilations of the global temperature of the Earth put together by many different studies, and it turns out that that doesn't make much difference. There's not a lot of difference between one and another. There's no way you can make the warming since the 70s, which is sort of the smoking gun for human impact on climate. There's no way to make that go away by getting rid of urban heat island effect kinds of things. So it's a real effect, but it's not why the Earth is getting warmer, and it doesn't seem like it affects how much warmer we think it's getting as attributed to the fossil fuels, to the greenhouse gases. Okay, the next one is about sea surface temperatures. So there was this transition in the sort of technology of measuring sea surface temperatures from measuring them in buckets of seawater that you tie a rope on a bucket and put it over the side and get it back. Actually, it's perilous to do this. I've done this from a ship underway, and the bucket, usually it sort of skims on the top of the water, but then occasionally it lands just right and kind of digs down, and it'll pull your arm right off. It's an amazing thing. I had to go out, and part of my job on this particular cruise was to measure temperatures and actually CO2 concentrations. I was bringing the water back into the lab and making these chemical measurements, and so I had to go out on deck by myself at night to do this thing, and they were very careful to tell me, tie the rope to the railing, don't tie it to your arm, because we'll never see you again. Anyway, so sea surface temperatures measured from a bucket, are they going to be too warm, too cool, or just right? They're going to be too cool, because evaporation from the outside of the bucket carries away latent heat. Just the way our perspiration keeps us cool, carries away latent heat that you need this heat to make a gas from a liquid. It's sort of the same. And this actually did turn out to be a significant correction. So when they put together the sea surface temperature record, there was actually this blip right at the end of the Second World War, and turned out to be a fairly big correction for about 0.5 degree or something for these different kinds of measurements. The other kind of measurement is in the engine cooling water that gets pumped through the ship all the time. So I want to make the point of sort of comparing relative climate changes in terms of the global average temperature. So I've got a series of questions here that are all have the same options. Less than 1 degree C, about 1 degree, about 2, about 3, or about 5. And we're going to talk about a couple of different, flavors of climate changes. And so how much the temperature has changed since sort of 1950, yeah, the answers there that you have going are about right. It's actually probably less than 1 degree, so maybe 0.7 degrees, something like that. But sort of on the low end of this spectrum for sure. And how about over the last 1,000 years? So we got the Little Ice Age going now and the medieval warm time. Little Ice Age correlates with a time of no sunspots. So it's thought to be mostly the sun was just kind of in a cool mood that particular couple of centuries. Medieval warm time, they don't know sunspots because there weren't telescopes in medieval time, but there are these proxies for the intensity of the sun, which are the beryllium-10 and the carbon-14 that get made from cosmic rays. So the sun is bright, it's got a stronger magnetic field, and it shields the Earth a little bit more from these cosmic rays, and so you get a little bit less of this beryllium-10 and carbon-14 depositing in ice cores, which is where they measure it. So this is an example of a proxy. You know, we don't have a satellite from medieval time measuring the intensity of the sun the way we can do it today. Sunspots, kind of a proxy for the intensity of the sun. And then these cosmogenic isotopes are another proxy for the intensity of the sun, something that goes back further in time. Anyway, so yeah, less than a degree or 1 degree C. The Little Ice Age was maybe 1 degree C colder. It sort of depends on which reconstruction you're looking at, but on the order of a degree C. Medieval warm time was maybe a ½ degree C warmer than the long-term average. So again, temperature changes of about a degree. So the temperature changes since 1950 are sort of comparable to the ones from the last 1,000 years. And you know, the medieval warm time and the Little Ice Age weren't the end of the world, but they were sort of noticeable to, you know, our agriculture and stuff like that. And you know, the warming that we've seen so far is also not the end of the world, but it's noticeable if you live in the right places. It's not really so noticeable here, but in Alaska, you know, or the Antarctic Peninsula or other parts of the world, the warming has been much more intense. And so, you know, it's sort of noticeable, but not like apocalyptic, a 1 degree sort of temperature change. Glacial cycles, glacial interglacial cycles. How much temperature change is there between the glacial world and today? So glacial world, huge ice sheets in North America and Northern Europe, and sea level 120 meters lower, and Europe, to the extent that it wasn't covered in ice, was a occasionally inhabitable steppe. You know, it was like wicked tundra. Occasionally people would venture out there during climate, you know, during mild times, and then they would retreat back during colder centuries. It turns out that the temperature changes between the glacial and today are about 5 degrees centigrade. So that astonished me when I first heard it, because it would seem to me like it'd be much bigger. I mean, the glacial world looked different, you know, from space. It was a different planet. The climate, especially in the northern hemisphere, but everywhere, was noticeably different. The snow lines in the mountains were lower. You know, it was a drier planet. There was less methane because there was drier, and so there were fewer swamps to make methane. You know, it was a very, very, very different climate. And that was on the high end of the spectrum, about 5 degrees C. And so then finally, the forecast for business as usual for the coming century, where does that leave us about how big of a temperature change? And you should sort of remember that from the 6 degrees book, although 6 degrees, which Mark Linus takes as the top end of the IPCC range, you know, that's just that. That's the top end. The best, you know, the middle forecast for the coming century under business as usual is maybe about 3 degrees C or something like that. But you know, it's possible that it could be higher. So the basic story is that the coming century is kind of a different animal than the climate changes we've seen so far, or in the last 1,000 years, or even, you know, since the development of human civilization, which goes back to, you know, 8,000 years ago, but definitely is after the end of the Ice Age. So the climate changes, the warming, the temperature changes going to the end of the century under business as usual are putting us kind of in the domain of the glacial interglacial cycles. That's kind of the caliber of the climate changes. So the last lecture today is on, you know, what to do about all of this. The fancy word for it among people that talk about this a lot is mitigation. Sort of how to avoid climate change. So then the partner word that goes with this that you always hear, one versus the other, is adaptation. So you adapt to the climate changes, or you mitigate, which means you avoid them. You clean up and don't let them happen. So to start with, I want to talk about, because you can read in the newspapers now about negotiations, what everybody's proposing, various bills in the House and the Senate, and the Copenhagen, negotiations, and what other countries are talking about. So I wanted to put all that into context by talking about how much CO2 is too much. And so why CO2 in particular? You know that the extra methane in the atmosphere is warming the planet some, and there's nitrogen, N2O, laughing gas, and there's freons and other things. But why CO2? Well, one is that it accumulates as opposed to methane. So if methane was destroying the world, then we could just clean up the methane system and things would recover in a decade or something like that, because that's the lifetime of methane in the atmosphere. So that's less of a sort of a long-term commitment. Whereas CO2 accumulates in the atmosphere, as you learned in that lab and in class here. So this is, and it's also, CO2 is more than half of the warming forcing. So all these conversations tend to focus on CO2, and then they put the other greenhouse gases as kind of, oh yeah, because there are ways. I heard that the main contribution to global warming from New Zealand, for example, is methane from sheep, and they could just feed the sheep different stuff and clean up. So it's not like these other gases are unimportant, but CO2 is kind of the big one. There are more sheep in New Zealand than people. Sounds wonderful to me. So the first sort of, I don't know sheep very well, so maybe I wouldn't. The first way that people started talking about this was CO2 concentration stabilization scenarios. So they would come up with some, hypothetical CO2 in the atmosphere with time going up and then leveling off at some target. So this target could be 350 or 450, 550, 750 is starting to get up to business as usual. Uh, 550 is about doubled CO2 concentration from the natural. So 280 times 2 is about 560, I guess, would actually be doubled CO2. So when I first started, reading about all this, the benchmark that everybody was after was what has to happen in order to keep CO2 from doubling. That was kind of like what everybody thought the goal had to be. So to do this, you've got to go from emissions to some CO2 concentration, and you need a model to do that, because some of the CO2 that's released dissolves in the ocean and goes into the land and things like that. So the way this worked a decade ago was there would be this concentration trajectory, and then you'd figure out what the emissions had to be in order to match that trajectory. But then in the last 5 years or so, the conversation has sort of shifted to temperature targets. And the one that you hear the most is a warming, average temperature of the Earth increase by 2 degrees centigrade. So 2 degrees C would be warmer than Earth has been in thousands of years, in probably hundreds of thousands of years, going back to through the time that's covered by the ice cores. So it's just sort of a number to talk about. It's a problem because people sometimes talk about 2 degrees C as like a danger limit. And that leads you to conclude that 1.9 degrees C would be safe. And that's not so clear. It's just sort of a dividing line between where things still sort of look like the Earth that we know, and when they start to go totally totally out of sort of our experience. It's just sort of a scale of the problem to talk about. It's not really a danger limit, but it's just sort of what would it take to get to 2 degrees C just to have something to kind of talk about. And there are people who say that dangerous stuff is already happening on Earth, like the droughts in Australia and the American Southwest, and the melting of the sea ice in the Arctic. And the Earth is only warmed by less than 1 degree C already. So, to say it would be safe to go all the way up to 2 is obviously cavalier. But it's just a number to sort of talk about, as long as we don't forget and think that it means that, that's like safe below that. So it's sort of now seems like it's making this kind of more complicated, because now we have to go from emissions to a CO2 concentration and then to a temperature. So it's like adding, and you got to have a model for this too. So as our understanding kind of increases, we can kind of be a little more, and the temperature is kind of closer to what actually, hits home. What really hits home is probably more to do with water and storms and sea level and things like that than actual 2 degrees C of temperature. You've read the 6 degree book, so you sort of know what the kind of thing you're talking about. So ultimately, it would be nice to go all the way to impacts and then, set some impacts. Like we don't want the storms to get stronger than this, or droughts to get more severe than that, or something. But we haven't really gotten there yet. So this temperature threshold is kind of the state of the conversation. And actually, even though this this series of going from emissions to CO2 concentration to temperature is now sort of a longer chain of like cause and effect that we have to sort of figure out. It actually, looking at it in terms of temperature, turns out that it kind of simplifies things in a way that what matters most is the total slug of CO2 ever released. So when they were doing these stabilization scenarios, where the CO2 concentration goes up and then sort of levels off at some level, there's kind of ambiguity about how you do that. You can you can make lots of cuts now and then keep emitting for longer and reach that level sort of later, or you can, you know, go business as usual for now and then cut quickly later, and it makes, you know, you're getting to the same place, but, you know, it's sort of slippery how you get there. There's ambiguity about sort of how you get there. But it turns out that there's not much difference between CO2 released now versus CO2 released later when we think about the maximum temperature. And that's because CO2 released now, let's say you release a bunch of CO2 in the air all at once, and then it sort of decays away. So this would be like an airborne fraction of some slug. Like you're going to decide whether to burn a tank of gas to go visit your parents or whatever over Thanksgiving. So you put that in the air, and it kind of decays away over say 100 years. And when the warming is going to be most intense is sort of at the end of the century. So that means that CO2 released today might give you less warming in the year 2100 than CO2 released in the year 2099 or something like that. But on the other hand, it takes several decades for the Earth to warm up from CO2. So the fact that this CO2 has been kind of pulling on the climate for decades, by the end of the century, kind of means that CO2 released now is kind of equivalent to CO2 released later. It doesn't matter so much when you do it. The main thing is how much you release by the time you stop. It's sort of, there's this sort of cancellation effect that it turns out that if what we're after is the total, the maximum temperature, it doesn't make so much difference if it's released now or later. It's just a question of whether it's released or not. You had a question.
What's the label for the y-axis?
Airborne fraction. So let's say that we dump a gas tank worth of CO2 in the atmosphere this afternoon, for example, driving down Highway 65 in my case. So by the time I get there, 100% of the CO2 I release will be in the atmosphere. So that would be there, 100%. And then over 100 years or so, you know, maybe half of that would dissolve in the ocean, so that by the year 2100, only half of the CO2 that I release will be affecting the temperature when, you know, things are starting to get, you know, the warmest. But on the other hand, it's what I release has been warming the planet for a long time. It warms up the ocean, and so the heat sort of builds up. And so it turns out it doesn't matter that much if I release it today or the year 2050 or 2030 or what. Now is the same as later. And that really makes things a lot simpler because then, you know, it's this very simple balance that, I mean, for regulations, if you release stuff now, you can't release it later. So there is a figure in I put a little supplemental reading about this on the chalk site, and it has a figure right here. So we've got, this is emissions of carbon, and it's growing exponentially, like in the Kaya identity, you know, model that you played with. And then starting at a particular time, we start cutting the CO2 emissions by some, you know, percentage per year. And then the total slug of CO2 that gets released is like the area under this curve. So you got to imagine this curve going back through time, and there's some area that you add up how many years of how many gigatons a year of emissions, and you do the whole thing, and you get a number in gigatons. So if we start now, we can sort of glide down towards zero with a fairly gradual, a few percent a year, and the area under the curve will be, equal to some slug of CO2 that will keep the Earth from, passing that 2-degree temperature target. If we wait later, then we've accumulated more CO2 in the air, and then you got to cut more quickly until finally by sort of the year 2040, you'd have to cut everything in just a few years in order to keep the area under the curve from exceeding to give you too much warming. So if you take the percent per year cuts that are required and plot them as a function of the year that you start making the cuts, if we cut now, we can do a very manageable a few percent per year. So that means, kind of gradually replacing power plants as they get old or whatever. But if we wait longer, then you gotta do things in a more drastic way. So the more cuts you do per year, that's more stuff you gotta build. So it's like I heard somebody say it's like you assign a paper. Students have to write a paper, like a term paper for the class, and you have a kind of a flexible deadline. So you say the paper will be due on Monday and it'll be 10 pages long, but if you want to do it, hand it in on Wednesday, that's fine, but then it's got to be 20 pages long, or you can wait till Friday if you want, but it had to be 30 pages long. It's like, you're running into this wall where the sooner you start, the less effort it will take to sort of get there, if that makes any sense. I saw the look of horror in everybody's eyes when they heard about this, so that got through, I can tell. So what does it take then to do these kinds of cuts? There's sort of several different sort of perspectives or ways to come at this. The most kind of conservative and businesslike comes from the IPCC. We've talked about the IPCC before. It is this sort of framework under which scientists are, collaborate on writing and reviewing these chapters that talk about climate science to try to inform the political side, right? And so pretty much the whole class has been on what was called in IPCC Working Group 1. So Working Group 1 was about the scientific basis. And so they published these reports, and if any of you wanted to read, details about what hurricanes are going to do or sea level or whatever, there's chapters and summaries and things you can download from this that talk about the scientific basis, why climate should be changing, and so on. There's also Working Group 2, which was on impacts, which is basically like 6 degrees. I can tell you 6 degrees is a more colorful read than the full IPCC Working Group 2 volume, which is 1,500 pages or something like that. And then there's Working Group 3, which is on mitigation. So there are summaries and there's chapters about agriculture and transportation and buildings and industry and waste disposal, forestry, all different kinds of things that affect CO2 emissions. So if you have some need to look at this in depth, this is sort of like a great source to go. And they compiled cuts of emissions that are available for a threshold cost of $100 per ton of carbon dioxide. And so this is kind of a projection for the next couple of decades. It's kind of not assuming any brilliant new inventions, no breakthroughs, just kind of what's available today. And so I'm just going to write a sort of a short table here. One entry is on energy supply. So this is where you got your windmills and things like that. Different ways of generating energy. And they say you could cut about 1 gigaton of carbon per year. Now, one thing that's tricky, and I apologize for it, is that there's this weirdness with units. So a ton of CO2 is not the same as a ton of carbon, and it's endlessly confusing. Real chemists like to count atoms rather than weighing them, so that 1 mole of carbon reacts with 2 moles of oxygen atoms, or 1 atom reacts with 2 atoms. Then it all kind of makes sense. But this isn't driven by chemists. This is driven by, I don't know, economists or something. So we've gotten sort of stuck in these weight units. And so a ton of CO2 is not the same as a ton of carbon. And so you sort of have to pay attention to that a little bit. Anyway, a gigaton of carbon per year could be cut by changing the energy supply for $100 per ton of CO2. The total fossil fuel emissions, you'll recall, are about 7 gigatons per year, so 7 of these units. So energy supply, building windmills, can cut some off the top, but it can't cut it down by most of the way or anything like that. Other entries in this table, there's transportation, which is also about 1 gigaton per year. And there is buildings. So heating and air conditioning and lighting, ventilation, all use energy in buildings. And that could save about 1 gigaton of carbon per year. Actually, buildings are kind of unique in that much can be saved at no cost, because the cost of putting in better insulation will pay for itself in saved fuel costs. So some of them, it would actually be a negative cost if you could save money and cut emissions. So the building sector is sort of unique in that, it's got all this, what they call low-hanging fruit. Really easy, cheap cuts can be made. And then there's also in industry, they find about a gigaton of carbon per year could be saved. And then finally, the last one, agriculture. Another about 1. So the take-home from this table is that there's no single thing that can save the world, no single change. We can't just drive more efficient cars and then everything is done. But since CO2 comes from all these different things that people do, different parts of the economy and human endeavor and everything, there's no single cut that can be made or single change that will sort of solve the problem. It has to be over all the different sources of carbon. And another take-home message is that, at least for the near term, efficiency is by far the cheapest way to cut CO2 emissions. So not windmills, but hybrid cars and compact fluorescent light bulbs. So there's all these different ways. It's never been a problem before. We've always had sort of all-you-can-eat energy, and so it's never been an issue that the way we use energy is terribly inefficient. The fact that the lights are probably on in this room 24 hours a day, nobody cares because electricity is sort of cheap and it's not been worth turning off the lights. But at least for the coming decades, increases in efficiency have a lot more scope to kind of change CO2 emissions than changes in energy supply. So windmills and solar cells and stuff like that, important, but they're not the be-all, end-all. So that's the IPCC, which is very heavily reviewed and very, very kind of down to earth and practical, and if anything, maybe a little bit sort of on the conservative side because it is so heavily reviewed. The science is also, if anything, a little bit on the conservative side. On the kind of more visionary end, there's this guy who was just at the university a couple of weeks ago and gave a talk named Amory Levins. And he's sort of an efficiency guru. He consults. He's got this company that it gets jobs to design energy strategies for factories and the military and houses and things like that. And he comes up with these extreme increases in efficiency. So for example, he says that if you use 4 times the insulation required by the code in a building, then at some point you can use a much smaller furnace. And so if the extra insulation is going to cost you money, and the normal way to engineer this is to say, if I put in more insulation, is it going to save me money in fuel? And then you just put in insulation until you don't get any more money from it. But if you go just totally over the top with insulation, then suddenly you can use a much smaller furnace, and then the money that you save on the furnace can help pay for the insulation. And so he kind of is like extreme energy efficiency. He claims that his house in Aspen, Colorado is heated by a 150-watt Labrador Retriever. He doesn't have a furnace, and it gets 30 degrees below zero there for days on end, and his house manages to stay warm because it's so incredibly efficient. So it kind of reinforces the point that efficiency is kind of the way things can go. So and then putting this into the sort of social world, the world of the rest of the industry and population and politics and all that sort of stuff. That's where hot, flat, and crowded comes from, or fits in. So, hot is self-explanatory. That's about the climate change. Crowded is population. Flat comes from this idea that Friedman has been, tooting on his horn for a long time of globalization. So, if standards of living are very different in India than they are here, then companies can send jobs to India and get stuff done more cheaply. And what that does is it brings up the standard of living in India and brings it down here a little bit. And so it kind of is a great leveler. So globalization is kind of leveling the playing field and the standards of living and sort of what's expected out of life in various parts of the world. And that's important because Americans use, we got like 5% of the population, and we release 25% of the CO2 in the world. If the rest of the world tries to live like Americans, if everybody everybody lived like us, it would be something like 5 times our current sort of carbon footprint. So it's as if the population of the Earth went up by a factor of 5. In terms of energy use and CO2 emissions. And the Earth is teetering on how much can it do already, and multiplying what our footprint by a factor of 5 globally sounds catastrophic. So the fact that globalization is tending to even the playing field, if everybody wants to live like us, it's a disaster. So the way that Friedman and other economists kind of frame this is in terms of what they call external costs. So if we burn a gallon of gas, we pay some taxes and we pay the cost of drilling for the oil and refining it and all of that. But the damage to the to the climate, especially in the deep future, that's not part of our decision. So there isn't we don't pay for that. So that cost is external to sort of our decision making about whether to release fossil fuels. And so the solution to what this does is it distorts the market. So economists worship the free market, and it does seem to be a very powerful thing. But the free market has blind spots if there are things that are impacts of our decisions that are not kind of within the realm of economics. If we're not paying for the damages, then we don't take them into account, and it's sort of like the market then has a blind spot. So the way to make this work is to internalize the cost, and you do that by either a carbon tax or by a strategy called cap and trade. And so a carbon tax is fairly straightforward. And for a carbon tax, the price is known in advance. So if you're the CFO of some company, it's kind of useful because you know how much you're going to have to pay in carbon taxes every year. So it makes it kind of easier to plan financially. The trouble with carbon tax is that the emissions are sort of unknown in advance. So you put $1 a gallon carbon tax on gas. How much does that going to change how much people drive? The only really way to know is to try it and see, which you can do. The other possibility is called cap and trade. So this worked brilliantly well, actually, for reducing sulfur emissions from coal power plants in this country. So they sort of said, okay, the total amount of sulfur that can be emitted by all the coal plants is going to be some amount, and you can emit this much and you this much. But if this plant needs to emit more and this plant can emit less, they can sell the right to emit the sulfur. So it's like selling permit to pollute. And the economic theory is that the plant that is located really far away from low sulfur coal, where it would be expensive to clean up, for them it's worth paying to buy the right to emit. And another plant where it's very cheap to clean up, it's in their interest to clean up even more than they have to and then sell the permits to this other company. So the idea is that cap and trade uses the market to find the cheapest way to avoid the emissions. So cap and trade then is sort of the opposite of a carbon tax, in that the price is kind of the thing that floats and is sort of unknown to start with, but the emissions are well known because that's just the cap. And then the price is unknown because you have to trade for it, and so there's a market like the stock market or something. So Friedman has all kinds of interesting ideas about how sort of the politics of this all can kind of play out. And he's a political guy, a newspaper columnist, and I'm not, so I can't really do justice to his thinking other than asking you to read. But in general, in the U.S., he says regulations are very effective and necessary, but he says that the devil is in the details. So I went to a hearing that the EPA had it was last week, I guess, where citizens were allowed to sort of make their, what they said they wanted to say about whether the EPA should start limiting CO2 emissions from large power plants. And when EPA regulates emissions from power plants, there's this amazingly huge loophole that plants that already exist are exempt from the regulation unless they upgrade. It's called new source review. So if you build a new plant, you got to use the best practices. But if you've got an old one, you can kind of grandfather in. So that's a loophole big enough to drive the whole coal industry through. And so that's the kind of detail, something that a non-policy person like myself might not have thought about at the start. There's a really interesting chapter in there about China. I've never been to China. I don't understand China very well. It seems like a very kind of mysterious world politically. But he characterizes it as the leadership there has this sort of bargain with the people that they can lead as long as the people are prosperous. And so it was easier, he says, to kind of open up to a free enterprise sort of system there because that led to prosperity. But now transitioning from there to a kind of a clean free enterprise system is hard because everybody wants to make money and they don't want to deal with or comply with environmental rulings that come down from on high if they can get away with it. So he claims that what is required is a sort of civil society like exists in this country where people can bring a lawsuit if some company is polluting. A sort of empowered citizenry can sort of police that. So he thinks that the necessity to clean up not just global warming but also sort of air pollution in China will have impacts on the sort of openness of the society. Now, he's been wrong before on international things. It's not like everything he says is gospel, but still, it's an interesting thought. So I guess I would finish by saying that, the 6 Degrees book is terrifying, and reading Hot, Flat, and Crowded and thinking about how much has to change in order to avoid climate change, it makes it seem really daunting. Like, can this really happen? But on the other hand, if hypothetically we lived in a world where there just was no more coal, if we were running out of coal just because there was no more, it wouldn't be an issue. It's not like we'd be going back to live in the Stone Age. There'd be the price of coal would go up naturally. It wouldn't be anybody's political agenda. And it would be, a no-brainer to come up with new energy. So the only difficult thing I think about climate change is negotiating sort of the cooperation to leave the coal in the ground. You have a question?
Do you think Friedman is overly optimistic or accurate in suggesting that with better regulation, people will be motivated in the U.S. to adopt and create better, cleaner technologies?
I think he's probably right that if you make the market such that people are paying the cost for the CO2 emissions, you internalize the climate damage, sort of levels the playing field, and I think there's lots of innovation, lots of stories about great ideas that people have. So I'm hopeful that he's right about that.